Good morning, Ferry.
I can see you, so I hope you can see me.
Good morning. Do you hear us?
Yes.
Excellent, excellent. So apologies for leaving you there. There was a
No
very
problem.
interesting subject. So we'd like to welcome you again. The last time you were with us was 2019 in the same room.
Exactly.
Now using the new technology of online systems, but it's great to see you again.
Thank you.
Okay. So the floor is yours. You're the boss now. Please take the lead.
Thank you.
Thank you.
Thank you for your kind introduction. Thank to the organization for having me over. I apologize that my Turkish is a bit rusty, so I will do the presentation in English. I hope the translators will not have a problem with that. So let me start sharing my screen. Again, welcome. My name is FERRİE van HATTUM. I'm a professor at Saxion University of Applied Sciences, but mostly I'm in charge of the Thermoplastic Composites Application Center, as you can see in the image. And today I will talk about the efficient use of thermoplastic composites. So no thermosets for people who like so much epoxy and other thermosets. This will not be your happy hour. On the other hand, there is a lot of promise in thermoplastic land, but just a small introduction for what we are and where we are. On the picture on the right-hand side, you can see where we are based. We are at the very eastern part of the Netherlands, almost on the German border. We are part of the University of Applied Sciences, so I don't know exactly if you have this distinction in Turkey, but at least in Germany and in the Netherlands, we have, let's say, academic universities, and we have what they call in Germany Fachhochschule. They train an applied kind of engineer, both equally useful to the national economy. I'm running a research group within a University of Applied Sciences, but as opposed to a typical research group at the academic university, our research group TPAC is completely self-supporting through our research projects that we run with industry. And as Dutch industry is 90% based on SMEs, small and medium-sized businesses, this is typically what we run our projects with. So we typically have a group of 50 plus SMEs, mostly regional, but also national and some international, that in changing partnerships, we run our projects with. And when I say SMEs in the Netherlands, we are typically talking about companies, let's say 15, 20, 25 people working in a company. So it's really a small sized company, and that will later on probably also explain the way we approach our research. So normally, like I translate it, our research group is basically the R&D department of the smaller and medium-sized businesses. Therefore, most of our focus in the research group goes towards cost-effective use of thermoplastic composites, because that's the most critical part in thermoplastic composites. A large part of our efforts, as you can see on the right side, go into research into the processing, because a lot of the processing equipment and technologies that are available are suitable for aerospace, under development for automotive, where you have large volumes for the downwriting of the equipment. But for many applications for SMEs, you need to go to a more cost-efficient way of processing. So a large part of our efforts go into developing new processes. The next step is then making it work with real industrial equipment like, well, I hope you can see the one behind me. This is what we call automation. So when one of our processes or whatever is stopped or under development, it needs to communicate with the production cell. So it can be integrated in your typical industrial process with a typical cycle time below 1 minute. And finally, on the third logo on the right-hand side, you can see our recycling efforts. Increasingly, like from what I understood from the previous speaker, you can see that the environmental burden of our activities become more and more important. Hey, Europe 2030, Europe 2050, I'll come back to that later. And we see a demand growing from our clients in recycling options, both on the plastic side, where composites can be a good option, but also from recycling composites themselves. And a good example both of the recycling activities as well as our hands-on, more applied approach of a research group I show in this picture. I hope you can all see it. As you can see, and on the top side, there is a flying object. I think by now I can mention what it is, but I prefer not to in order to avoid problems. But anyone who is handy in Google can easily find what we are looking at. We ran a program together with the partners that you can see on the logos on the right-hand side in order to use the scratch material that was produced during the making of the tail section of this flying object and reuse it into body panels of exactly those same tail sections. So the whole project was developed from scratch, so a wild idea at the drawing table, to in-flight demonstrated panels, including happy clients, within 2 years. The process that allowed for the recycling without fiber breakage and good mixing of these parts was completely developed in-house. The panels themselves that are on the tail sections, they are 100% recycled, which is a world first. So there is no virgin composite material there. And the most impressive part in this case is that we managed to do all of this with 80% CO2 emission reduction, but also 9% weight reduction, which is strange because the recycled material, shorter fiber, random orientation, in principle should have lower properties than the virgin material. And the trick there is, of course, in the stiffness that you can see in the picture in the middle, because in the process we use, which is something like a compression molding process, you get the rib stiffeners for free. And as people in aerospace know, most of the applications are stiffness driven. So that gave us an angle over the virgin material. So your recycled part actually performs better in weight performance, and in overall performance they are the same than the virgin material part. And also because we reduced the processing time from, well, you can see our machine from 1.5 hours in autoclave, out of autoclave, to minutes, we reduced the total panel cost by 70%. So the current production is only roughly a third of the cost of the original production. Now, this is very much aerospace, and as I told you in the beginning, we don't really do that. So I will immediately skip this slide, but it's a nice example of how we approach projects. This is what we typically focus at. So I hope you can see a moving image at the top. At least in my case, it is moving. This is what people typically know composites from. A nice Boeing airplane where carbon really is the only solution for many parts. But the relatively high price is, let's say, doable, although it's under pressure, in the aerospace sector. However, in the Netherlands, although we have some strong companies in that field, we don't have that much aerospace industry. We do, however, have a very strong plastics industry. Now, that's completely the opposite side of the spectrum, but you can see some examples below. Has very simple waste bins, injection molded office furniture. On the right-hand side, you see even a walking pavement of completely recycled plastics. All of that still amounts up to quite a significant part of our national industry, but most of these industries, they are unaware of the potential, and the technology of composites is not there yet to be used in this kind of application. It's easily to be seen that if you want to replace the legs on the furniture you see in the center, that the stiffness of virgin plastic is simply not enough. So if we can introduce composite stiffeners inside plastic products using the same machinery, the same molds, the same processes, that definitely has added value for the industry. So that is what we focus at. And one of the central machines we use for that is what you can see behind it. In our case, it doubles as an injection molding as well as a compression molding machine. And I show a process of overmolding where a 0-90-degree pre-consolidated thermoplastic material goes in the oven. It's heated. Therefore, it becomes drapable. The previous part goes out of the mold fully automatically. You can see the molten prefab going into the machine. I hope the film is running smoothly. In the meantime, the previous part, which is, I believe this is a braking pedal, so seriously loaded parts, is taken out of the machine, while the next part is being molded and over injection molded with thermoplastic resin. So a similar machine together with Engel and Engel R&D in Austria, we acquired, adapted to our needs. You can see it's in lab. So the process that we developed, like I told before, including the recycling process that you've seen on the flying object, it needs to run on this machinery, because if we don't finish it on this machinery, then it's not ready for industry. And what we intend to do in our center is whenever we are done with it, industry can go for it in, let's say, series production. So we do up to 0 series, something like that. Now I get to the point of, let's say, efficient use of thermoplastic composites, because in the previous movie, and like in many composite applications, typically you find that we roll out a layer of 0-90 or plus or minus 45 continuous fibers over the whole structure. And depending on the education you've got, at least I was always told, I'm a mechanical engineer, that the blessing of composites is that you put the fibers exactly where you need. Now, this is typically not the case in most structures, but it makes sense in way of processing that you just pull out the 0-90 degrees pre-preg material. But if you had the complete choice, you would rather do something like lightweighting. As you can see, the picture on the left shows how you can save 60% on weight on an exactly the similarly loaded structure just by optimizing the fibers into the load path. But that is almost pure mechanics and mathematics. And then on the right-hand side, you see typical product. This is one of those armrests that is in the back seat of, let's say, a BMW or Mercedes car that you can put down and also put your skis through. Near Bavaria, they have a lot of mountains. The left one is the metal version, as is. It's roughly 4 kilos of weight. The right one is the same parts, but structurally optimized. We did that together with our partners of the Technical University of Chemnitz in former Eastern Germany, but in Germany, where you can see the ribbing system. That already saves them more than half of the weight on just one automotive part. And together with them, we looked into locally providing the stiffeners, but then with continuous fiber reinforced thermoplastic. For that, we needed to develop some processes, and it's basically what we call 3D printing of continuous fiber thermoplastics. Now, it doesn't look all too beautiful, but it works. What we basically did is, on the right-hand side at the bottom, you can see a very simple 3D printing head that we modified, put on our machinery, where pre-impregnated continuous fiber tapes can be printed in any shape. Now, this film has already some age. The quality in the meantime has improved. On the left-hand side at the bottom, you can see that we mounted a minimized head of that on a robot. So basically, we can print all kinds of inserts for these overmolded products, but still to convince smaller companies moving a robot or controlling a 3D printer somehow for some of them is a bit too complicated. So we even developed something really simple, which is at the top end of the slide. It's a handheld composite fiber applicator. Now that might sound pretty silly, but as you can see on the left-hand side, this is the company that made these walking pavements that I have shown in the first slide. They have a problem with sagging. So there's crossbars made of fully recycled polypropylene, but under the heat and the sun, under their own weight, they will start bending. This is not good for your application, of course. You get complaints, or you need to replace, or you need to over-dimension them. With just a couple of strips on the backhand side, on the back side of those beams, the whole problem of sagging was solved. So we are now we demonstrated that with a simple hand applicator on the spot. We are now in the process of integrating exactly that in their continuous extrusion process. But the core here is the development of a 3D printing technology, very cheap. We downgraded it so much that in the meantime, any commercially available, let's say $300 3D printer, modified with our printing head and the material we use, but it can be any prepreg, could do this job. And then also the cost of composite processing goes down rapidly. So it's perhaps not the fastest process, but for 2,000 euros, you roughly have 10 of those printers standing and doing the job for you. So that's relatively easy, and it's actually robust. Why do we do that? A very simple example. This is a cable sheath. So it's a round piece of typically steel, but we have a company that makes this smaller series in rim nylon. So it's basically meltable and curable thermoplastic nylon. Steel cables run over them, so you'll find them in big cranes when you are in the construction site. There's a lot of them at the back, a lot of them at the front, and so that's a huge weight. And it's at the top of those building cranes, so you can imagine that lowering weight there is critical. But they are heavily loaded structures. So what you find in applications like this is that the stress concentration, as you can see in the picture at the left bottom side, is highly concentrated around the central axis, and that's exactly where all the load enter and when it rotates. So at some time, simply due to creep inherent to thermoplastics, the wheel will start running like that. So the whole crane becomes unstable. What we then defined, we made a flower-looking kind of insert, integrated that into this application. Through the fibers, the force is distributed over a larger area, so locally the stresses became lower, and as you can see at the top right-hand side, they were able, where before they could only use this kind of technology, a piece of plastic versus the steel alternative for the smaller dimensions, they could gain a little bit versus the steel alternative, saving a factor of 4 over the weight, because, well, let's face it, steel is good stuff, but it's really heavy, and replacing it by reinforced nylon. But this has only been possible by integrating a 3D printed flowery insert. The problem with locally reinforcing your parts to optimize the weight saving is that you introduce inhomogeneous into your part. So I show this with a very simple part. If you have a piece of plastic which is working fine, if you can introduce composite, your stiffness and strength might increase with a factor of 10 or 15. However, if you do it in the wrong way, you can see it on the right-hand side, as the composite is not shrinking, but the plastic is shrinking a lot, you will create curvatures. And people in plastic land know this. There's nothing worse to process than a simple flat part. And especially by introducing composites into plastics, exaggerate this problem. So that is something we really need to look into, but there's a lot of simulation slides that I will go rapidly through. Do not worry. We looked into current simulation software, just also to keep it a very low profile. Most of our companies and students, the engineers we train to work in the companies, they are familiar with SolidWorks, and then there is the plastic simulation part of it. So we took that design and simulation software package, very, not nifty finite elements, but very low level simulation software. And we were able to predict the kind of effect that you see into bending, but also into the shrinking of the part. If you look in close detail, I don't know if it's visible on your end of the screen, but in the picture on the right-hand side in the center, you can see one strip that is white and another tensile bar that has 2 composite strips like a sandwich in there. And if you look carefully, you can see that the polypropylene one actually shrank 2-3 millimeters more as composed to the composite reinforced one. So that's something you need to take into your equation, especially when you start. Remember the midsection of the car. If you have these complex creations with local reinforcement, in the end, your whole part might be doing this. You don't want it. A lot of considerations where to place the fiber, in which quantities. We do a lot of simulation and optimization schemes. In this specific case, it was a foldable crate. So if you have crates for transporting apples and oranges, etc., they're typically injection molded, polypropylene, polyethylene. But I believe there is 2 million of those crates just from one supplier continuously rotating in the business. So you pick your oranges from the orange tree, you put them in the crates, you stack them 20 high. You can imagine if I can have local reinforcements in the crates, all of a sudden the stiffness of the crate goes from 1, let's say, to 10 or 20. We can stack them twice as high. The transportation is more efficient. They arrive, in our case, in the Netherlands, where they are inside cooled storehouses, very expensive square meters. If you can stack them higher, you need less square meters. So the business case for this kind of very technical application is easily made, but you run into the same problems as I've shown before, shrinkage and warpage. So a lot of these crates, next time you are in a supermarket, have a look at these crates. They are very complex in shape. So we optimize the shape as to locally introduce these reinforcements. We came out with a version that does not warp and actually gives you the promised stiffness increase. And it's working on an injection molding machine just like the one I show behind. So typically what we're doing, back to something that is most likely more your kind of background, an automotive application. This was a demonstrator we worked on together with the Technical University of Chemnitz in a merge European cluster of excellence. It's a crash barrier beam. My personal favorite material is glass fiber polypropylene because it's very cheap, it's widely used, you heat it up, you cool it down, and it's always brilliant, but especially the crash performance is good. So what we did in this specific project, we took out a crash beam of I believe it's a Volkswagen door, but it doesn't matter. It was the original steel one. We redesigned it in plastics, and the first one on top you can see without reinforcement. It was a long fiber injection molded, over molded part, so there's organo sheet on the outside. We did exactly the same thing, but then introducing locally the light blue lines at the bottom, local reinforcements made out of UD tapes. We tried 3 different versions that you can see on the right hand side in the center. Fully reinforced, only the center section, or absolutely minimized just in the middle. And if we then look at the performance, we can find that by just adding a small reinforcement, we can get a 10% load increase of exactly this structure. Stiffness increase as well, which is good, so you get less intrusion during action, but the physical work, so let's say the energy absorbed by the structure, remains the same. So basically, by introducing small reinforcements, you actually improve the performance of the part at only a minor increase, well, in this case, in weight and costs. And then I will come to an end because I see it's 10:26, at least on my watch. So that's 11:26 your time, I believe.
Thank you.
Yeah, you're welcome. Just to show what this has accumulated in. So right now in our lab, we cover the whole development scope from base materials together with a tape supplier. We can make any kind of continuous fiber reinforced tapes that then we can locally weave either in organo sheets, the 090 pre-consolidated sheets, or we can make 3D prints. And in the end, we can make, well, a completely integrated part like this in the machine you see behind me. Typically 1 minute cycle. The part exists of an overmolded organo sheet shape. The edges as well as the center, they have local reinforcement 3D printed on a robot set, pull through the sections in the middle. This is the ordinary, glass fiber polypropylene variant that is currently, it's the most widely used material in automotive industry. The same part, basically, we developed with, in another project we ran with Stellantis. Coming back to the recycling part, this is the same part, but then made out of over 50% of post-consumer polypropylene waste. So it's really completely recycled polymer. It resulted in the final part with roughly the same mechanical performance, having over 50 weight percent recycled polymer. And this is already anticipating future EU directives that the automotive industry is expecting on mandatory recycled content, the 2030, 2050 kind of legislation. It's the same part, very similar performance, and it was all developed in-house. So we're seeing how we can further go follow up on this with Stellantis. The tape itself was, we partnered with a Dutch company, Comptape. So we have the virgin one, it's this one. Then we replace the polymer by recycled polymer because the fibers are doing the work. And then the next step is this one. Actually, we did this with a Turkish company called Biprek. They supply continuous fiber reinforced PP as well as PLA, so bio-based composites. In the picture, I must admit, I'm lying a bit because yesterday I was looking for the correct picture. I say it has local stiffeners. As you can see in the picture, this specific picture does not have, but I can guarantee you, if I would have found the other parts, we keep on losing them for some reason, it's here. We can do exactly the same as we've seen here, but now with PLA, a bio-based, biodegradable polymer, plus a flex fiber. In organo sheets, the inserts were made out of that material, and we overmolded it with the same material. Actually, you can see the little sticks on the top left-hand side. They are the pultruded sections that we then 3D printed to integrate in this part. And we have now a part that is, of course, not the same overall performance. We need to do a re-engineering design because flex fibers, they have lower stiffness than glass fiber. But you catch my drift. Technologically, it's possible. And in this case, you have the 100% biodegradable variants. So with that, I will leave it to this. What we try to do in our lab is very much balancing between what can materials do, how do we need to modify production, and how we need to close the loop with the design, because in the end, it's all about the product and especially about the costs of the product. Any more info, please have a look at the website. You can look at our LinkedIn or follow our Twitter account or just send me a mail. With this, 10:30 exactly, 11:30 your time. Thank you for your attention. If there's any questions, I'm afraid I will not be able to hear them clearly, but I will do my best. Thank you.